This is a lecture about the overview of a compiler. So, in this lecture we will go through a block diagram of a compiler, look at the various phases of a compiler. For example, there is a lexical analysis phase, there is a parsing phase, there is a semantic analysis, there is intermediate code generation, code optimization, and also machine code generation. So, we will look at each phase with some examples, a minor description of what is happening, and so on and so forth. So, let us begin with a block diagram of what is known as a language processing system. So, in a language processing system, the source the source program, for example, goes through a preprocessor. For example, in a C program, you have a number of macros such as hash define, hash include, and so on and so forth. These are passed through the preprocessor. The preprocessor expands these macros and takes appropriate action at the compiler level itself, and there is no code generated for such macros. Such modified source program is then fed to a compiler. The compiler generates machine code. The machine code could be in the form of an assembly code, or it could be directly binary of the machine, etc., etc. In the case it is an assembly language program, it is fed to an assembler which converts it into the machine language of the target machine, and then such modules are produced probably individually, and therefore a linker or loader is needed in order to combine such modules, and finally the loader gives out a complete relocatable, all these combined together will be the task image of the machine on the and this can be run on a machine. So, for example, if you look at the compiler itself, which is a block in the previous diagram, it has these phases. This is our mainstay for the entire lecture. There is a lexical analyzer, there is a syntax analyzer, semantic analyzer, intermediate code generator, machine independent and machine independent code optimizer, code generator, and then machine dependent code optimizer. These are the phases of a complete compiler. You can say these are in some way parts of the machine itself being the compiler. So, what does each one of these phases in a compiler do? That is what we are going to be looking at in the rest of the lecture. So, for example, the lexical analyzer, it takes the program which is given in the form of characters, right. The characters are all read from a file, and then the lexical analyzer diverts it into what is known as a token stream. So, why are these needed? We will see very shortly. The token stream is then fed to a syntax analyzer which checks whether the syntax of the program according to the programming language rules are all satisfied. If they are satisfied, it produces a syntax tree, otherwise it gives a number of errors saying that look, there is no then corresponding to the if then statement, there is no assignment symbol in an assignment statement, the plus is missing in an expression, and so on and so forth. The syntax tree itself is not the end. The syntax tree, for example, does not tell us that the program is valid. To give you an instance, if we are trying to assign an entire array, some value to an entire array, this is not permitted in C. And with such constructs, the syntax analyzer will not be able to point out the error and say this is wrong. So, what does the semantic analyzer, what does the syntax analyzer do in such a case? The syntax analyzer in such a case says, sorry, I can't help, I will pass on this information to the semantic analyzer, and that takes care of it. The semantic analyzer checks such mistakes, and then if everything is right, it produces what is known as an annotated syntax tree. So, the annotations are nothing but the semantic information of the program, such as what are the symbol names, what are the various constant values and so on and so forth. These are all set to the intermediate code generator, which produces an intermediate representation. Why this is required, etc., will be seen in the rest of the lecture. Then the intermediate representation itself is improved by the machine independent code optimizer. There are many chances for such improvement, as we shall see. And then the optimized intermediate representation is fed to the code generator. The code generator actually is specific to every machine, and then it converts the intermediate representation into machine code, and finally there is some more improvement possible on the machine code itself, that is done by the machine dependent code optimizer. Finally we get a very compact optimized target machine code. So now let us look at each one of these phases in some detail. So here is an example of what lexical analysis does. So let us take a very simple assignment statement: Fahrenheit equal to centigrade into 1.8 plus 32. There are characters in this particular assignment statement, F, A, H, R, E, N, etc., etc., and there are symbols such as equal to, star, plus, and so on, and there are numbers such as 1.2 and 32. The lexical analyzer converts such stream of characters into slightly more meaningful, what are known as tokens. For example, Fahrenheit and centigrade are names. So they are traditionally called as identifiers. And what exactly is the identifier? That value will be stored in a symbol table. So ID comma 1 and ID comma 2 will denote the two identifiers Fahrenheit and centigrade, 1 and 2 being the indices of the symbol table in which the names are stored. Similarly, the equal to itself is called as the assignment operator, and it is given a token as a sign. Similarly, the mult op and the add op. So the constants are given the tokens f const and I const with the appropriate values. What exactly are these tokens? Inside the compiler, the token itself is represented very compactly as an integer. So because of this, the space required for storing the entire assignment statement will be very small compared to the storage which is required by the character stream. Lexical analysis is very cumbersome, so if you try to write it by hand. So lexical analyzers are typically generated automatically from regular expression specifications. So there are two tools which are very well known for this purpose. One of them is called Lex, which is available on every Unix machine, and Flex is the counterpart of Lex, which is available from GNU. The tokens of the lexical analyzer will actually become the terminal symbols of the context-free grammar, which is parsed by the parser. We will see this a little later. Lexical analysis is usually called as a function to deliver a token whenever the parser needs. It is not as if the entire stream of characters is converted to a stream of tokens and then the parser starts its work. It is actually called only when it is required to deliver a token. Why is the lexical analysis separate from parsing? Theoretically speaking, there is no reason to separate lexical analysis from parsing. In fact, as we shall see very soon, lexical analyzers are specified using regular expressions. So regular expressions can in fact be written as regular grammars, which are nothing but a special form of context-free grammars. So therefore, a parser typically, its specification, for example, can be written inclusive of the lexical analyzer itself. But there are reasons why we make the lexical analyzer separate. First of the reasons is the simplification of design. So this is a software engineering decision. The compiler is a huge piece of software. Therefore, making the entire software into modules actually enables good software engineering practices. So, one of them is to make the lexical analyzer separate, similarly the parser and so on and so forth. Then the input output issues are all limited to lexical analysis alone. For example, this is one of the modules of a compiler which does intensive I/O. The program is in a file and it is in the form of characters. So, each character has to be read and then fed to the parser. So, the lexical analyzer might as well do this entire part, and it is possible to design the software very efficiently for such I/O. There is no need to bother the rest of the compiler once the input output is taken care of by the lexical analyzer. Lexical analysis is based on finite state machines, finite automata as they are called, and such finite automata are far more efficient to implement than a push down automaton which is used for parsing. Why? It is well known that to parse a context free language sentence, it is necessary to have a push down automaton, and the push down automaton uses a stack. So, if we actually convert the entire lexical analyzer specification into a context free grammar, then there would be a huge number of pushes and pops corresponding to the character stream of the source program. So, this is very inefficient. We might as well do the pushes and pops on larger pieces of the source program, which are logical entities called tokens. So, this makes the parser much more efficient. So, these are some of the reasons why lexical analysis is separated from parsing. So, let us now look at LEX in order to understand how it does lexical analysis. This is a very trivial simple example of a LEX program. What it does is it simply recognizes capital letters A to Z in the whole program. Now, let us look at some of the details of such LEX programs. So, whatever we have written here is called the A to Z plus is called a rule, and what we have written below it, the YY wrap, the main, etc., are the program segments. So, let us look at some details of LEX. What is the form of a LEX file, a LEX specification? LEX has a language for describing regular expressions. So, I mentioned this already. It generates a pattern matcher for the regular expressions described. How does it do it? It actually converts each of these regular expressions to finite state machines and then arranges this in the form of a pattern matcher. So, we will look at some of these details very soon. The general structure of a LEX program is simple. There are some definitions which are nothing but shorthands, and then we have a marker in the form of two % symbols. Then we have the rules, the patterns or the regular expressions. Finally, there is another marker in the form of two % symbols. Then we have some of the user subroutines which are supplied by the user, and a LEX compiler generates a C program called lex.yy.c as its output, and this can be used either by a parser or it can be used on its own. So, we will look at two examples where it is used as a function by the parser and another example where it is used as a standalone program. Now, to the definitions section. The definition section contains definitions, and it also includes code that is supplied by the user. For example, the definitions are like macros. They are not regular expressions on their own, but they are used in writing regular expression specifications. Digit, for example, 0 to 9. And what is a number? Number is a single digit followed by 0 or more digits. So, digit star implies 0 or more digits, as is usual in the regular expression notation. Included code is all code which is included between the two markers percent flower bracket and percent flower bracket. So, for example, float number int count 0 is a piece of code which is applied by the user for some initialization purposes. What does the rules section have? This is the heart of LX specification. It contains patterns and it contains C code. A line starting with white space or material which is enclosed in the markers percent flower bracket and percent flower bracket is all C code. This is very similar to the C code which is included in the definition section as well. And then anything else, if a line begins with anything else, it's a pattern. So, pattern lines contain a pattern and then some C code. So, pattern action in C code, we will see examples of this. That is how it is written. The C code lines are not processed by the LEX compiler at all. They are just taken and copied to the output. The patterns, they are regular expressions. So, they are translated into non-deterministic finite automata, NFA. These are then converted to deterministic finite automata because it is difficult to implement NFAs. These DFAs can be optimized. Why? There is a very famous theorem which says all the DFAs, all forms of the same DFA can be converted to the minimal form. The state minimization theorem enables this, and these DFAs are all stored in the form of a table and a driver routine. Now, the action associated with a pattern is executed when the DFA recognizes a string corresponding to that pattern and then reaches a final state. This is very similar to what happens in a finite state machine. You start off from the initial state, then you feed characters to the various states, then the transition happens, each transition leads you to a new state and finally you reach a final state. So, when you reach a final state, you have really recognized that particular pattern and then you can actually do some action. Here is a nice simple example of LX program which is used as part of an expression parser later on. So, there are actually many of these tokens which are recognized by this particular LEX specification. There is a definition section which shows two definitions, right. There is a number definition and then there is a name definition. The number definition simply defines a number. The first part is 0-9 plus then a backslash dot question mark. Well, looks difficult, but it trivially says the number is any number of digits followed by a dot which is an option. Then there is a bar. So, the bar says either this or that. So, number could also be 0-9 star followed by dot and then followed by 0-9 plus. So, in other words, the meaning of that is any number of digits followed by a dot followed by any number of digits again. Only thing is it makes compulsory to have a digit after the dot if the dot is present. So, similarly, the name itself could be A to Z, capitals, A to Z, small, followed by any of the letters A to Z, small a to z, or any of the letters and numerals 0-9 any number of times, that is the star. So, we are really looking at letter followed by letter or digit star. Now, the regular expression number, once it is recognized, it has a small action following it, which is the scanf. So, what does the scanf do? The scanf really takes the text of that particular token, right, that is the number, the the numerals which make that number, but it is still not in binary form. So it reads it into a variable called YYLVAL. YYLVAL is a variable which is generated by Lex. It is already known to us and it is understood by Lex as well. And this YYLVAL is principally used to transfer the values from the lexical analyzer to the parser. For example, here we are reading a number, and later in the parser for expressions we will use the value of this particular number. How do we communicate the value from the lexical analyzer to the parser? That is through the variable YYLVAL. And return number says the token which is generated is number, and that is returned by this particular function, the action piece, a piece of action code. So whatever is written in capitals, for example, number and name, post plus, post minus, these are actually tokens, and as we will see very soon, these tokens are really defined in the parser, and the lexical analyzer is supposed to recognize and pass them to the parser. The second one, the name, there is a little more processing which is done here. Now once name is recognized, the symbol table is looked up. Symlook actually with YY text. So YY text is the text of the name itself, the characters corresponding to the name. Symlook is the symbol table routine. It looks up the symbol table routine, and then if it is already present, it actually gives you a pointer to it. If it is not present, it will insert the name into the symbol table and return its pointer. And what is YYLVAL? In this case, YYLVAL is actually the pointer value itself. YYLVAL.simp is nothing but the pointer value, which is a pointer into the symbol table for that particular name. And what is the token? Token is the integer code name which is returned by this action code. Similarly, for double plus it returns post plus, for double minus it returns post minus, and for the end of file dollar it returns a 0, and any other character including new line it simply returns the character itself. Here is a second example which is slightly more complicated. The previous example was called as a function by the parser, whereas this is a program on its own. What does this particular program do? I will skip to the next slide and then get back to this in a minute. Look at the bottom of this slide. It gives you examples of C declarations. Int a, comma b10, c, comma d25, float k20, l10, m, comma n. So now it may be clear. It actually recognizes such declarations. So you must understand that not everything in a Lex specification needs to be actually, let me take that back. Whatever we describe in the syntax of a programming language as a context-free grammar is not necessarily always context-free. It can even be specified in the form of regular expressions. That's what I want to show here. For example, we have blanks, which is nothing but a blank or tab any number of times, a letter, digit, then identifier, number. These are all the usual tokens that are recognized by a Lex specification. But here comes the next one. We are still in the definitions part. So array declaration part is actually an identifier followed by right bracket followed by a number, which is nothing but the number of dimensions of the array followed by the right square bracket. Whereas a declaration part is array declaration part or just a simple name. A declaration list is a list of such declaration parts, and a complete declaration says integer or float followed by blanks followed by a declaration list followed by blanks again. So this is the declaration which actually is parsed by the lexical analyzer, a Lex specification that we have written here, and these are all legal specifications. So, once a declaration is found, it writes it into the text file, declaration is found, it writes it into the text file, and then ignores all the others. So, it writes it into a text file called declaration file and ignores all others. So, the rest of the Lex specification is simply in the main program you open a file and call YYLex, and in the YY wrap you just do the wrapping routine, close the file and get out. So, this is an example to show that it is possible to use Lex to parse even sizable parts of a programming language specification such as declaration. But I must hasten to add that not every declaration is so easy to parse within a Lex specification. So, some of these can be. I hope it conveys the essence of a Lex tool. Now, let us move on. Let us talk about syntax analysis. So, the lexical analyzer returns these tokens, right, the same assignment statement that we considered before: id, assign, id, multop, fconst, addop, iconst. These are all our tokens. So, fconst is the floating point constant and iconst is the integer constant. These are fed to the syntax analyzer. The syntax analyzer makes sure that the assignment statement is indeed correct, in syntax. So, in other words, there is an integer, there is an identifier on the left side of an assignment, there is an identifier on the right side of an assignment, followed by an expression or whatever operator, and so on and so forth. In general, the programming language constructs are complex. There is if then else, there is for loop, and so on and so forth. The lexical analyzer does not worry about such constructs. It simply returns tokens for most of these constructs. For example, if it is if then else, it returns if, then for the entire expression it returns a number of tokens followed by then, and followed by the number of tokens for statements, and so on and so forth. The syntax analyzer would look at the stream of tokens that is coming into it. It uses a context free grammar to check whether the rules are all appropriately satisfied. So, and then it constructs what is known as a syntax tree. So, here is a syntax tree for the assignment statement. The assignment has left child as an identifier, the right child as a plus operator, the plus operator has left child as star, and its right child is the constant, and then the star operator has identifier on the left hand side, and then the constant 1.8 on the right hand side. So, such intermediate syntax analysis trees are produced, syntax trees are produced and fed to the semantic analyzer. So, now syntax analyzers can be generated automatically from context free grammar specifications. So, as I said, context free grammar is the basis of parsing. A push down automaton is constructed from such a context free grammar specification, and then it is fed a sequence of tokens, and it continues. There are many tools which can do this. For example, Antler is a tool which takes LL1 context free grammars and produces a top down parser. Yacc and Bison. Yacc is a tool with Unix, and Bison is the corresponding tool available from GNU. These take LLR1 form of context free grammars and produces a parser for such grammars. These parsers are all deterministic push down automata, but the main problem with these parsers is they cannot handle any semantic features of programming languages which are known as context sensitive features of a programming language. For example, if you have variables in the program, obviously you would have a number of them. To check whether your variables have been declared before they are used in the program is a context sensitive feature. You really cannot check whether it is possible such a declaration exists. Secondly, whether the left and right sides of an assignment match is something that we really cannot check in a context-free grammar and using a push-down automaton. The reason is for a context-free grammar and a push-down automaton which is produced by it, whether the left-hand side is an array name or whether it is a simple integer name is not known. That information cannot be captured in a context-free grammar. Therefore, checking whether the right hand side also happens to be an array of values or whether it is a simple arithmetic expression producing an integer value cannot be checked by the same context-free grammar. For doing this, we need special types of grammars called attribute grammars, and we will see a simple example very soon. Third example of a context sensitive feature is the regarding parameters. You would have a number of parameters in a function, and you would actually put down the declaration of the function and its parameters and then call the function with the actual parameter list. Whether the types of the parameters in the usage match the types of parameters in the declaration is a context sensitive feature. This cannot be captured in a context free grammar, and therefore we need the next phase of a compiler called the semantic analyzer phase. A syntax tree, as I said, will be produced as the output from a syntax analyzer, but I must add that this does not always happen. In some cases, if the entire compiler is a one pass compiler, in other words it produces even the machine code in one pass, it is not necessary to produce the syntax tree explicitly. But if there are language constructs such as in C++, which says okay, you can use the variables and put the declaration elsewhere, perhaps much later, that is possible in the class in C++. Such constructs cannot be validated semantically in a single pass. We need to produce the syntax tree, decorate it with some of the semantic information available from the program, and pass this entire thing to the semantic analyzer for validation. So that is really what we need to see next. So before that, let us see how a parser specification is written for a very simple expression parser. Let us use Yacc for this. Yet another compiler is the expansion of the acronym Yacc. Yacc has a language for describing context free grammars. The productions are all going to be described by this particular language. So, and it generates an LALR1 parser for the context free grammar that we described. So, its description is very similar. There are declarations very similar to that of Lex. There are declarations which are optional, then the rules or context free grammar productions which are compulsory, and then some programs. Now, what is important is that Yacc uses the lexical analyzer generated by Lex with great ease, and it the terminal symbols of the context free grammar which are specified by Yacc should actually be produced as tokens by the lexical analyzer. Finally, Yacc generates a file called y.tab.c. So this is a Lex specification for the expression parser that we already saw. It has number, it has name, then post plus, post minus as its tokens. Here is the Yacc specification. So to begin with, there are some declarations of a symbol table, and then a routine called symlook, and then there are some include statements. These are all part of the user code which is applied, and now we start declaring tokens. So we will come to this union a little later. There are tokens called name, number, post plus, post minus, and then we have this equal to, plus, minus, star, slash, then unary minus, then post plus, post minus, so many of them, right. And we have also talked about the left associativity and right associativity of some of these operators. So tokens are name, number, post plus, post minus, and equal to, plus, minus, star, and slash. So it says equal to, plus, minus, star, and slash are left associative, and it says u minus, post plus, and post minus are all right associative. U minus is right associative, post plus and post minus are left associative. Then it is possible to attach some semantic information to non-terminals and terminals. For terminals such as name and number, there is a deval field which is described in the union statement above. It's a double field, and this sim field is a pointer into the symbol table. So for numbers, double is the declaration of the value of the token, and for names, a pointer into the symbol table is the value of the token. And for non-terminals such as expression, the again deval, which is double, is the semantic information associated with it. So here is the specification. Let us look at expression to begin with. Name equal to expression, that is the assignment statement, and expression plus expression, expression minus expression, expression star expression, and expression slash expression. So these are all the right hand sides of the various rules, and then of course parenthesis expression, parenthesis, minus expression, and there are some more in the number, number post number, number post plus, post minus. These are the various right hand sides of the productions. The left hand side is common, that is expression. Okay. So expression going to name equal to expression, expression going to name. This is the way to read this particular grammar specification. What is happening here? Lines is nothing but a couple of productions added to make sure that the calculator does not stop prematurely. It will actually be going into an infinite cycle until you press some strange characters. So the Yacc specification also has an action part here. For example, name equal to expression. It says $1 pointer value is $3 and $$ is $3. So $$ is the value of the left hand side symbol expression. $1 pointer value is the value of the token name. $3 is the value of the expression in the right hand side of the production, name equal to expression. So this simply says the value of the left hand side non-terminal expression is nothing but the value produced by the expression on the right hand side, which is fine with us. That is the way it should be. Similarly, expression plus expression says the value of the left hand side is $$ equal to $1 plus $3, which is the sum of the two values produced by the two expressions. So this is the way it continues. This is just to give you a sample of how Yacc specifications are written. I am going to skip the symbol table routines because they are not really important for our discussion. Okay. After the translation, from syntax analysis part of the translation, we move on to what is known as the semantic analysis. In the case of semantic analysis, the input to the semantic analyzer is the syntax tree, and which has information from the program. Finally, it validates this particular syntax tree along with the information available from the program, and then produces what is known as a semantically validated syntax tree, which is the input to the next phase of the compiler, namely the intermediate code generator. What is semantic analysis? So, semantic analysis handles actually the features of a program which cannot be handled at the syntax level. So, as I mentioned, type checking, whether the left hand side of an assignment is the same as the right hand side of an assignment, the types I mean, whether I am wrongly assigning an array some value which is not an array, or am I assigning a character value to an integer variable. These are all the kind of checks that I want to do in semantic analysis. During semantic analysis, we also need a huge table called the symbol table, which stores the names of the variables, their types, the parameters of functions, their types, dimensions of an array, and so on and so forth. This particular symbol table is useful not only during compilation, but also for other purposes such as debugging. So, for example, when you turn on the debugger in GCC, the compiler actually includes the entire symbol table in the assembly code which is produced by it. That is how actually the debugger can know what is a variable, which variable is it, what is its type, and so on and so forth. Otherwise, it is impossible for the binary code to find out the types of such variables. The specifications which can be used in semantic analysis can be provided by what are known as attribute grammars. And attribute grammars can specify what are known as static semantics of programming languages, but not dynamic semantics. Dynamic semantics is what happens at runtime, that cannot be specified by attribute grammars, and there are no suitable specifications for these either. We will have to actually generate code to check such violations in the code itself. It is possible to generate semantic analyzers automatically from attributed translation grammars, and we will very soon see an example of how this can be done. For if declarations need not appear before use as in C++, semantic analysis actually needs more than one phase. It may not be possible to do this semantic analysis in just one phase, we may need more than one phase. Here is an example of an attribute grammar. To begin with, we have a context free grammar. So, S going to E going to E plus T, or T, or or it is a let expression. So, let ID equal to expression in expression, etc., etc. And then we have a non-terminal T going to T star F or F, and finally F goes to parenthesis expression parenthesis or number or ID. What are the specialties of this language? This language actually permits expressions to be nested inside another expression. So, we have nested expressions possible, and we can also have scopes for the names inside these expressions. Here is an example. Let A equal to 5 in let A equal to 6 in A star 7. So, the inner A has this restricted scope of let A equal to 6 in A star 7, and the outer A actually cannot interfere with A star 7, the expression A star 7. So, the inner A rules there, and the outer A rules only in the outer level of the expression, that is the entire expression 5 in let A equal to 6 in A star 7 minus A. The second A is actually 5. This evaluates correctly to 41, provided the scopes of the two instances of A are treated as different. So, if the inner A retains the value 6 and A star 7 is evaluated with that 6, and if the outer A retains the value 5 and it is used for the outer A, then the value of the expression is 41. So, such an attribute grammar requires a symbol table for such a programming language of expressions requires a scope symbol table for implementation. So let us see how an abstract attribute grammar is used to specify such a language, and then see how this works. So abstract attribute grammars use what are known as inherited attributes and synthesized attributes, whereas Yacc permits only synthesized attributes in its specifications. So here is an attribute grammar. The first production is S to E, and the attribute grammar format is simple. The context free grammar rule is written, followed by the attribute computation rules. The attributes with a down arrow in front of them are inherited attributes, and the attributes with up arrow in front of them are synthesized attributes. For example, in the first production, E.SymTab is inherited, and S.val, E.val are both synthesized. So the rule corresponding to the production S going to E is very simple. It initializes the symbol table to a null symbol table, and it says whatever expression is produced by E is the value produced by S as well, S.val equal to E.val. Let us directly go to the next production, E1 going to E2 plus D. E1 and E2 are the two non-terminals, instances of the non-terminal E. So here the whatever is inherited from E1, for example here this is E1, it has a symbol table coming in, and that is given to E2 as a symbol table with which it should operate, and that is also given to T as the symbol table with which it should operate. So that is why there are two statements, E2.SymTab equal to E1.SymTab, and then T.SymTab equal to E1.SymTab. By the way, I should also mention that the order in which these statements are all written does not corresponding to a sequence of statements. The order of executing these statements is actually found out later by an attribute evaluator. What is the value of E1? E1.val is the value which is nothing but E2.val and T.val added together. So similarly, let us take the most complicated expression E1 going to let ID equal to E2 in E3. The value of E1 is the value of E3. So that is why E1.val is E3.val. And the symbol table for E2, which has all the names including ones from outside, is nothing but E1.SymTab. But the symbol table for E3 is very different. The symbol table for E3 is the symbol table of E1 with the name E2.val pair overriding any similar name within E1.SymTab. So this operator backslash is nothing but the overriding operator that we are going to define. So if there is a name inside E1.SymTab which is same as id.name, that name is temporarily overridden by this particular new id.name, and the new id.name will have the value E2.val associated with it. So this is the structure of the symbol table, and let us now look at a simple example to see how exactly the attributes flow. So the productions which are used here are two of them, S to E and E going to let ID equal to E in E. So here is a complete syntax tree for this particular sentence, let A equal to 4 in A plus 3, a simple sentence. The productions are S to E and then E going to this entire thing, right. So that happens in several steps. S E going to, it actually says let ID equal to E, okay, in again E. So this is the first level. Then this E expands further to T and then F and then number. This E expands to E plus T and then finally to T, F and A. On this side it expands to F and 3. So this is the syntax tree. We begin with a null symbol table. The null symbol table is handed over to E. It is also handed over to this side E. This side the symbol table continues to be null or empty, and when we get 4, the value is actually handed over to F, which in turn goes to T, which in turn goes to E, and this side the value which is handed over as phi, the symbol table value which is handed over as phi, actually now gets updated. So let's see how. Here is A, right? So now once we say this is 4, which is actually synthesized from E to T to F to 4, and the identifier A which is already available are combined into an association A to 4. This is the overriding operator. So phi overridden with A to 4 is the new symbol table which is given to E. That symbol table continues to be handed over to its successors. So A to 4 is the new symbol table which goes down, and as A to 4 goes down it meets another A. So E to T to F to A. So during F to A there is a symbol which is produced here, A. This A produces the value 4 when it is looked up in this particular symbol table, and the value of 4 goes up, right. So and the number 3 goes up without any difficulty, it does not need a symbol table. So these two numbers are combined into the value 7 because of the production E going to E plus T. So the values of these two are added, 7 is produced here, and this 7 is passed on to the root as the value produced by the start symbol. So now we can go through this little more. So for example, we saw that F2 number, the value of F is nothing but the number itself. So the number value is passed on. What is the value of F2? What is the semantics of F2 ID? So F dot val is the value produced by looking up this particular name inside the symbol table F dot symtab. So what is the value of T to F? Well, whatever value is produced by F is passed on to T. And what is the value of T to T star F? So we take the value of T2 dot val, take the value of F dot val, and then we add up these two values, and that is the value which is produced as the value of T1. So this is the way the attributes are computed, and then they are passed on to the start, the symbol. How are these translation grammars implemented? Let us say we consider Yacc. So in Yacc, how do we implement such translation grammars? So the most important thing to observe is that these are all very simple, and these can be read and understood very easily. Because they are very similar to what we had before. The symbol table is going to be a global structure here. And the other important thing that we need to do is to make sure that we understand this production, which breaks the single production E going to let ID equal to E in E into these three productions, E to LB, L to let ID equal to E, and B going to in E. So in these two productions everything else happens. In this production there is a new scope which is generated, and the name is inserted with the new scope. And once we complete this entire instruction, entire production, the entries of the previous scope are deleted, the scope number is reduced, and we return. So in other words, this breakage of productions is essential because Yacc permits addition of rules only at the end of a context free grammar production, and further it allows only synthesized attributes. The inherited attribute, the symbol table, is implemented in the form of a global variable, and similarly, in order to make sure that it is available wherever it is used, we have to make it a global variable. These are the two reasons why we need to make the symbol table into a global variable. We will stop the lecture at this point with a picture saying that the next class we will be looking at conversion of the semantically validated intermediate, the syntax tree into intermediate code, and then look at what happens to intermediate code when it goes through the intermediate machine code generation phase and optimization phase, etc., etc. So, thank you.